This week and this class, the Wednesday and Friday, we are going to learn internal flows together. When it related to internal flows, what immediately come to your mind? Oil in pipes, right? Anything else? The liquid in the chemical vessels, or even how our blood comes from our heart and flows into a series of branching blood vessels. We would spend the entire week to learn the heat transfer exchange inside the for laminar flow or turbulent flow inside a pipe, and as we will see, we can apply everything we have already learned in external flows to create and obtain those correlations for internal flows. I would do a quick review here for our external flow. We have a surface here and a free fluid coming at university of U infinity, velocity of U infinity. It starts to grow the velocity boundary layer and can transit to turbulence, whatever, which depends for flat plate. We need to calculate the Reynolds number to see whether or not we will have turbulence, which is given by the velocity of the outer flow times the length of the plate over kinematic viscosity. And for this, if we see this as a velocity boundary layer, velocity developed from 0 to that of the outer flow within the boundary layer. And it can expand as much as it wants because nothing there constrains the boundary layer. That's for flat plate. For a cylinder or spheres, we have Reynolds number defined based on its diameter, which is given as that of the outer fluid times the diameter of the cylinder or sphere over that of the kinematic viscosity. And we know that for flat plate, the transition Reynolds number, the critical Reynolds number is more or less like 5 times 10 up fifths. Above this, we will have turbulence. Within this, it will be totally pure laminar flow. But in internal flows, let's consider hydrodynamic boundary layer first. Consider we have a pipeline here, and it has a diameter of d. The fluid comes in at the inlet. We will mark it as our origin. And here is the center line of the pipe. What happens immediately after the fluid comes into the tube?
At slowest at
the surface. That's because that's because of the non-slip condition. The velocity at the surface is 0, but then due to the viscous effect, the surface effect will get propagate into the flows at the expanding boundary layer. For this case, for hydrodynamic consideration, this is our velocity boundary layer, and it is symmetric along the center line, where the boundary layer keep growing, just as what we have in external flows. We know it has a boundary layer, right? So very similar to what we have as external flows, but where it keep growing, like here, to as much as it wants inside the pipes. Now, the two boundary layers, they are the same by symmetry, where gradually merge at the center line, and we term this point as the x FDH. That's a notation given by the textbook, which is fully developed hydrodynamic entry length. Once the velocity boundary layer, they collide with each other. After that, the velocity profiles, of course, zero at the surface. And as Wesley just suggested, maximum in the center line. Right? It obeys parabolic. This maximum in the center line, we denote it as Umax, and zero on the internal surface of the tube. After this point, the velocity profile keeps unchanged as it moves along the length of the tube. And we term this region as a fully developed region, or hydrodynamic fully developed region, because we only care about velocity profile now. Before this point, let's consider the velocity profile along this line across the cross section. We know that outside the boundary layer, the velocity remains at whatever it initially flows in as constant. And inside the boundary layer, zero at the tube internal surfaces. And it's almost obeys linear change. It looks like somewhat like a trapezoid shape, not parabolic. Before the point where the two viscous boundary layers collide. After this, the velocity profile fully developed as a parabolic shape, and it keeps unchanged along the length of the tube. So we term this region as the hydrodynamic entrance region, and where the velocity profile keeps developing, because at the inlet it's uniform and it keeps developing. Once reach our hydrodynamic fully developed entry length, then it gets entered in the fully developed region. Since after that, everything, the velocity profile remain parabolic and keep unchanged. Of course, the length of the the fully developed hydrodynamic entry length developed on whether it is laminar or turbulence. In internal flows, how can we define a Reynolds number to help us tell whether it is laminar or turbulence? Very similar as what we have in the external case. We will have some velocity here. We have based on the diameter as a characteristic length, and over the kinematic viscosity of the fluid. But the question here is, what should we put there as a velocity? Because in external flow case, we have a very clear defined U infinity. What should we put here as our velocity for internal flows?
Average velocity?
You answer all questions correctly. There is no mystery there. Yeah. Because velocity varies as we see and keeps developing until it reaches the full developed region. Smart engineers, they define a mean velocity. And the m here, um, is a mean velocity. And how can we relate the two it can be easily related to the mass flow rate, which is given by we learned this on the first class of second week. Density times the flow rate. And the flow rate is given by the mean velocity over the cross-sectional area times the cross-sectional area of the tube. So we have our mean velocity equal to the ratio of our mass flow rate over the density of the fluid and that of the cross-sectional area of our tube. By now, we don't emphasize it should be a circular tube. What we need is just its cross-sectional area. But for the most common case, if we have a circular tube, which means that our cross-section area can be easily calculated by 1/4 pi d squared. Right? And we will substitute it into our mean velocity, and we can get our Reynolds number for circular tubes. Given by the four times the mass flow rate over pi, the capital D is the diameter, kinematic viscosity, and the density of the fluid. This equation is general, but this one it is only valid for circular tubes. And as long as we already defined the Reynolds number, then we can use this as the condition to tell when will we have laminar and when will we have turbulence. So the onset of turbulence, what's the number of the critical Reynolds number, but for external flow, not for internal flow. Yeah, but does anyone know what's the critical Reynolds number for internal flows? In fluid dynamics, it's often used 2,100. But according to our book, textbook, we use a very similar value, 2,300. The onset of turbulence means the laminar will start to transit to turbulence. But to achieve fully developed full turbulence, the Reynolds number is more or less like 10,000. It's much higher than its onset value. Any questions so far? Okay, let's keep moving on. Then we are aware that for the main difference between external flow and internal flow is this entry length. This concept is only valid to internal flows, because for our external flows, the boundary layer can expand. Nothing constrains its growth. But for internal flows fluid inside the tube, the boundary layer, they collide. They remain unchanged as the radius of the tube. Now, let's consider laminar flow and we will utilize everything we have already taught in external flows. And based on our understanding on entry length, we will obtain those correlations tabulated in textbook just within one step. For laminar flow, which means our Reynolds number is smaller than 2,300. How can we calculate the length here, which is our entry length? We have our viscous boundary layer. It keeps growing, and at the hydrodynamic entry length is increased to the half diameter of the tube. So what can we write there to help us derive the how much x it is for laminar flow? Right. But for laminar case, it was given in the formula sheet we have, and we learned in our external flows. The viscous boundary layer is given by 3, the coefficient 3 times square root. We have kinematic viscosity here, x. In external flows, everything is clear. We use the U infinity, right? But when it's, let's see, when the two boundary layers collide, what's the velocity at that point? U maximum, exactly. So we use U maximum as an approximation. And when it's as the fully developed hydrodynamic entry length, the thickness of our velocity boundary layer is half of the diameter of the tube. That's it. Then we know that for once it's reach this region, velocity profile obey parabolic, 0 at the surface, maximum in the center. And when it is parabolic shape, its maximum, which happens at the center line, is twice as is mean velocity. You can derive by yourself because everything is as simple as a parabolic. Maximum here is twice the mean velocity. So for x, we just double each side, and we will get our fully developed hydrodynamic entry length, the ratio over diameter of the tube for laminar case is more or less like 0.055 Reynolds number based on the diameter of the tube and the mean velocity of the fluid. The exact solution given by our textbook, it tells us that the fully developed hydrodynamic entry length for laminar case is 0.05 Reynolds number. And this is our equation, 8.3. But the textbook, I went through that the entire yesterday. No derivation there. It does not tell us how you can obtain this correlation. But based on what we have already learned in external flows, we have our viscous boundary layer. And we understand what does the entry length mean when the two viscous boundary layers collide. And each of them has a thickness of half the diameter of the tube. By simply establish its equation, we can get to the correlation almost the same as the exact solution provided by our textbook, just by one equation here. So, this is just for laminar case. How about when our Reynolds number larger than 200, 300? What will happen for our hydrodynamic entry length? It does not have a very general, explicit equation like that, but by the textbooks give us that for turbulence, fully developed hydrodynamic entry length is more or less like 10 diameters. It is almost independent of Reynolds number, which is different from our laminar case. Any questions so far?
I thought that hydrodynamic entrance only exists in the laminar part.
No.
No.
It is defined just by two boundary layer collide. No matter it is laminar or turbulent, it can be turbulence here. Actually, the transition typically happens there. It can be turbulence, but I don't care. We only care where does it collide. Therefore, of course, for laminar and turbulence, they have different expressions, but they have the same definition with the two boundary layer. For hydrodynamic, two velocity boundary layer collide.